Essentially, what we are working on is an AI accelerator, and what we've done is essentially made an accelerator using RISC-V cores, and these are 64-bit RISC-V cores with a very wide SIMD data path, and we've been able to squeeze over 1,000 of these on a single chip. And these are actually fairly advanced multi-threaded cores that can run up to gigahertz. And the amazing thing is the power envelope is actually quite interesting. You would never guess that 1,000 64-bit cores would be able to run at something like 20 watts, but that's something that we've been able to achieve. They're meant to run essentially a lot in data centers as an accelerator for AI, very efficient inference. But we also have what we call our Maxion out-of-order core, which is a big high-performance RISC-V core that can also enable our chip to run in sort of an edge-based application where it's self-hosted. The small cores, we lovingly call them minions. They're very cute little cores, but very deadly. So we have about 24 billion transistors and 7 nanometer process. I'll show you a little bit more details about the chip. So this is, this is almost literally the floor plan. We have, what we call here is a shire, and it consists of about 32 of our minion cores. And we have a number of these shires adding up to around 1,088 total minion cores. Everything is connected together with this NOC fabric. We have LPDDR4X on the sides here, very high bandwidth to try to communicate with memory. We have a PCIe interface, and the way our chips are used is actually on a PCIe card as an accelerator that can go into a server, a typical 2U server. And then here we have, essentially miscellaneous I/O flash and, various other things. It's actually a fairly large chip, fairly complicated. We used a lot of hierarchy, as you can see, a lot of multiple instances. And the power envelope is actually, one of our amazing things. This is something that was really a ground-up effort. We started with the RISC-V ISA, which is simpler than a lot and amenable to lower power, down to logic design and very efficient algorithms. Even our floating point units are designed completely from scratch. And our first chip is actually in volume production today, which I think is another quite an achievement by the engineering team. And the way we accomplished that is, of course, very comprehensive checking. We used static checks extensively. And of course, we did a lot of traditional verification that Prakash had mentioned, emulation as well. Here's where we stand right now relative to some other solutions. This is a comparison we did of essentially the Intel Sapphire Rapid CPU versus an NVIDIA A100 and our ET1 SoC. So we are really about efficient inference, which means basically inference per second per watt, and this is a benchmark called ResNet 50, where essentially we are doing a little bit better than what's used a lot in the industry, the GPUs, and actually quite a bit better than the big cores. Some of the things that helped us was static checking and lint and so on and so forth. All of you have been through this. We've been through it many times, and what I found on past projects is that we tend to be a little bit hesitant to do static checks because they run kind of slow, they take a long time, they create a lot of noise, right? So what happens is this tendency that, especially for large designs, we run it infrequently, we put it off, we do it a little bit later. Then that leads to long reviews. And by the time we've run all this, now we're getting really close to tape out because you know, where do we put our static checks? We put them in the tape-out checklist, right? It's not something that's, you know, typically done up front. It's done a little bit later. So by the time you get here, you have long reviews and your manager is standing in your cube and saying, you know, when are you going to be done with reviewing those million, you know, warnings and errors that you got from Lint. And that puts us into, you know, over here where there are lots of violations. There are lots of waivers to be written. We put automation around the waivers, right, because we don't know how to handle all of those and read them all. And then the automation can go wrong and, you know, create errors, right? So this is a vicious loop that, you know, I've seen in many projects. And you can see that this method is actually high effort. It can actually impact the schedule, and it can actually be very error prone if you miss something, right? So clearly this is a problem to be solved. And we were actually able to you know, solve this problem, I think, pretty effectively using the latest tools. So essentially, if you have you know, static checking tools which are relatively low noise and fast runtime, then what we can do is actually enable lint checking and CDC and other things essentially on all check-ins, right? So if you guys are familiar with the concept of always alive, right? We've now extended that to always correct, right? Which is amazing, right? So all of our check-ins, you know, have the static checks run. That leads to incremental reviews, right? Rather than giant piles of violations, the feedback is direct to the designer who just wrote the code, right? So everything is fresh in his mind. He gets immediate feedback. He's able to fix it. And now we're in a situation where we can actually end up with no waivers, no errors, because very often it's actually easier to fix the problem than to go analyze it and put a waiver, right? So now we have the ability to go do that, fix it right at the source by the designer who created the problem. And you know, what helps us even more is having a quick way to debug and actually visualize what the issues are so they can be fixed. And then as we go up the hierarchy, we add CDC, we add RDC, and you know, again, it works sort of seamlessly with our you know, sort of the always correct sort of concept. From a you know, project resource standpoint, you know, a recent project that I was on, we actually spent probably you know, a month, you know, in a critical part of the project. You know, essentially doing all the static checks and getting through waivers and so forth. It was probably a couple of engineers full-time and, you know, a large part of the design team that had to get involved, right? All of that, I think, was pretty much saved as far as the resources and time because we did it, you know, we did it incrementally. Most of the issues can be solved by the designer in, you know, 5 or 10 minutes if they're presented up front. When a designer, right, let's say at the end of the day, he decides to check in his work, that's when it would get run. And depending on if he's, you know, checking in a module, block, you know, full chip, right, whatever has changed will trigger different checks. And so we run it essentially at every check-in. Some of the things that we found, the linting tool, Ascent Lint, was actually very helpful. It found a lot of the things that you would expect to find. Signal width mismatches, you know, enumeration types driven to 0, you know, so on and so forth. So many of these things your synthesis tool will find, right? It'll give you an error and crash. And then, you know, the physical design guy comes to you and says, hey, fix this, right? So that's a loop, right? That we now can largely avoid. And some of these issues actually don't even show up in that loop because the synthesis tools are getting smarter and they'll just run and work around it. But then it goes to place and route and there's a, you know, there's a DRC or something later, right? So this is actually extremely useful. And you know, obviously handling them up front is the best thing. And we were able to do this because this tool runs, Ascent Lint runs in about 5 minutes versus another tool that we used that took more like an hour, right? So an hour is really not acceptable for check-ins, but 5 minutes is no problem. CDC tool, we did find some missing synchronizers. And really, I think the best part of it was that there's a hierarchical flow. We didn't have to go and create black boxes, which can create other errors and create other things that need to be reviewed. So that was actually a really good part of the CDC flow. RDC, we actually ran that very late, but we did find some issues. We were finding some things that looked like fundamental problems, and we actually went back and changed our reset distribution so that we would just get rid of many of those sorts of issues. And it was about a month for initial setup and about a week to review the results. Now that we have it, we run it pretty much all the time. So there are still a few things to work on, I think. We found that the reading constraints for a very large hierarchical design was a little bit slower than what we had wanted. And then I think, for the future, I would like to see a voltage-aware RDC. We actually have, many voltage domains on our chip. There's a reset network that runs through many of them, and we have to be very careful, especially on power on reset, that all the power domains are actually sequencing properly in order to be able to get the job done. All right, so to sort of sum it up, this is the game we're in. We want to try to have the most efficient inference on the planet, if we can. The flexible programming model with RISC-V, right? We're very proud of the fact that you can actually just use out-of-the-box RISC-V tools to program our machine, which is actually sort of unusual in the AI world. Often, it takes a lot of, very low-level coding to be able to do this. And to be able to get this general-purpose programming model and very efficient inference is really, I think, our, crown jewel at this point. We run, essentially ML compiler stack, general purpose, and AI and beyond. It's another movie quote, I think. Highly scalable design, so if you just do the math, we would be able to fit something like 17,000 64-bit RISC processors in a 2U server with multiple PCIe cards. And 350,000 64-bit RISC-V cores in a single rack, and not bust the power budget, right? And we were first time correct because we used static checks, we used a lot of simulation, and all the advanced simulation techniques. All right?